In this video, we're going to start talking about how to solve trigonometric equations. So up to this point in Chapter 7, we've done all those different formulas for a bunch of different situations that you could have with trigonometric expressions. Now we're going to put this all together and see how we can use this to solve equations. So we're going to start this section with just some really basic equations. When you solve trigonometric equations, there are two types of solution sets. So your directions will either say solve on the interval 0 to 2 pi, or it'll say find all solutions. If the directions say solve on the interval 0 to 2 pi, it means that you're only looking at those angles in the first rotation of the unit circle. So you don't want anything negative, and you also don't want anything bigger than 2 pi. If your problem says to find all solutions, that's a little different. So once you find those solutions between 0 and 2 pi, then we're going to add all integer multiples of 2 pi to that. So it's like you're taking into account infinite rotations around the unit circle. So just as an example of a general solution, I've written one below. So we have theta is equal to pi over 6 plus 2k pi, where k is an integer. So let's break this down and just talk about all the different parts. So this pi over 6 would be like your solution between 0 and 2 pi. That should be open. This 2k pi is taking into account the period of the trig function. So for sine and cosine, you'll use 2 pi. For tangent, you'll use pi. So I have that written up here. So tangent and cotangent, you'll use pi times k. For sine and cosine, secant and cosecant, you'll use 2k times pi, or 2 pi times k. And then this funny little bit over here is just symbols for k is an integer. So this is important because we don't want to take fraction multiples of k, or no, fraction multiples of 2 pi. If we do that, then we're not actually going 2 pi. So the idea here is we want all of those coterminal angles to our original solution. For example, say it was pi over 6. So we want to make sure we're going entire rotations of 2 pi. So it's very important that we specify that k is an integer. When you do your homework on WebAssign, it usually does that for you. However, be aware that that would be expected on a test. So, so this is expected on a test. If I were to ask you to find all solutions to a particular equation. Okay, so let's practice solving some equations. So we're going to start by solving each of the following equations on the interval 0 to 2 pi. So first we have sine theta is equal to root 3 over 2. So what we're going to do is we're going to solve for theta, and the way we do this is we need to find a way to move sine to the other side of the equal sign. And we can do this by taking the inverse of sine on both sides. So we'll get theta is equal to sine inverse of root 3 over 2. So this is when section 6.3 comes back, where we should have learned our inverse trig functions. So what we want to do here is we want to think about what angle on the unit circle, or angles, has a sine equal to root 3 over 2. So if you remember when we did our inverse trig functions, we had some special rules about what quadrants answers can come from. When you're solving equations, we want to ignore those. So because we're looking on the entire interval, 0 to 2 pi, we don't have to worry about all those restrictions about sticking in quadrant 1 or quadrant 4 or any of that. So all we want to do is think about what angles going around the unit circle have a sine of root 3 over 2. And there's going to be two of them. There's going to be one in quadrant 1, and there's going to be one in quadrant 2. Because those are the two quadrants where sine is positive. So if you remember your unit circle value, for which value has a sine of root 3 over 2, that would be pi over 3. And in quadrant 2, that same like pi over 3 angle is 2 pi over 3. So our two solutions are pi over 3 and 2 pi over 3. Okay, so notice how we're tying a bunch of stuff together here. We're talking about inverse trig functions. We're talking about the unit circle, which hopefully you've studied because that was on test 1. And then we're also just having to put all that together. So it's a lot, but the more you practice, the more it should get a little easier. So let's try another example. Our next example, we have cosine of theta is equal to negative root 2 over 2. So same idea, we're first going to get theta by itself. So we're going to have theta is equal to cosine inverse of negative root 2 over 2. So now let's think about where on the unit circle we have a cosine of negative root 2 over 2. So negative cosines are going to be in quadrant 2 and quadrant 3. And a cosine of root 2 over 2 tells us that we're going to have a denominator of 4. So the angle with a denominator of 4 in quadrant 2 is 3 pi over 4. And in quadrant 3, we have 5 pi over 4. So those are our two answers. We have theta is equal to 3 pi over 4 and 5 pi over 4. Okay, let's try another one. So this one's a little different. We have cosine theta is equal to 0.65. And this one's different because 0.65 is not a value on the unit circle. So let's go ahead and solve this for theta. So we have theta is equal to cosine inverse of 0.65. So this is going to be one where we have to use our calculator. So I'm going to make a little note of that here. So calculator, and we want to make sure when we're solving trigonometric equations that we use radian mode. Okay, so you may have some very, very specific questions that ask for degrees, but for the most part, it will be in radians. So if they don't specify a unit, assume that your answer should be in radians. So if we make sure our calculator's in radian mode and we put in cosine inverse of 0.65, we should get 0.863 radians. Okay, so this is one of our answers, but now we need to go find the other angle because we know there should be two. So let's think about what this looks like. So we know that this is pi over 2, and we know that this is 0. So 0.863 should fall somewhere in here, because pi over 2 is a little bit more than 1.5 because pi is a little bit more than 3. So 0.863 should fall in quadrant 1. And that makes sense because the cosine is positive. Okay, so the other angle with a positive cosine would have to be in quadrant 4. So we need an angle down here. And what's going to happen with this is we're going to get this symmetry where the angle above the x-axis is the same distance as the angle below the x-axis. So this angle is going to be negative 0.863. However, we don't really like negative angles when we're solving equations because we want our angles between 0 and 2 pi. Okay, so the way we can figure out a positive angle is we can just say, well, we know that the x-axis we can think about as 2 pi. So our other theta will get 2 pi, and we want to subtract off that 0.863. And if we do that, we should get 5.420. Okay, so a coterminal angle to negative 0.863 radians is 5.420 radians. Okay, so these are our two angles. Okay, so just to recap, when you have to solve an equation using a calculator, it sometimes is a little more complicated just because you don't have the two angles memorized that should be your answers. Usually your calculator will give you one of the angles because remember we had that we had those rules with the inverse trig functions where they can only fall in certain quadrants so that you get one specific answer. But since we're thinking about the whole rotation, 0 to 2 pi, we're going to have a second angle in there somewhere, and it's our job to find it. So whether you have to draw yourself a picture or show some kind of work, I need to see that you can get that second angle. All right? So now let's talk about general solutions. So once again, if you have to use a calculator, always assume radians. But we won't need to use a calculator on all of these, okay? So you should only use a calculator if you have non-unit circle values, okay? If you have unit circle values, I'm going to expect an exact answer. So our first example, we have tangent of theta is equal to 2. So first, let's solve for theta. So we have theta is equal to tangent inverse of 2. Okay, and if we put this in our calculator, because a tangent equal to 2 is not a value on our unit circle, we get that theta is equal to 1.11 radians. Okay, so let's think about where this is on our coordinate grid. So 1.11, we know that pi over 2 is roughly 1.5, and we know that this is 0. So this angle must fall somewhere in here. Okay, so if we want to think about what other angle would have a positive tangent, it would have to be in quadrant 3. And basically what we'd be doing is reflecting this 1.11 across the origin. So you'd end up with this sort of, I guess, flipped upside down angle in quadrant 3. Okay, so let's think about how we can write this as a general solution. So we have theta is equal to 1.11 because we always start with our solution on 0 to 2 pi. And for tangent, we know that tangent's going to repeat every pi, or 180 degrees. And that makes sense because you notice how these two solutions that we got between 0 and 2 pi form a straight line. And we know a straight line is equal to 180 degrees if we're thinking about angles. So what we're going to do is we're going to take this angle of 1.11 and we're going to add pi k to it, where k is an integer. So what we're saying here is if we add pi, we're going around to the other side of this line, and then if we add pi again, we're going back up to quadrant 1, add pi again, we're going back down to quadrant 3, and so on. So we're constantly flipping back and forth between these two solutions just on different rotations of the unit circle. So your general solution for this equation is the following. Okay, let's try another example. So this next one, we have tangent squared of theta minus 3 is equal to 0. So let's solve for theta. So this is a little different than the ones we've done so far, but you're just going to solve for theta just like a regular equation. So we're going to add 3 to the other side. So we have tangent squared of theta is equal to positive 3. And then we can take the square root. So we have tangent of theta is equal to plus or minus the square root of 3. So when you're taking square roots, just be really careful and remember that you always have to put that plus or minus next to the square root. Okay, so now we can solve for theta by taking tangent inverse. So we have theta is equal to tangent inverse of plus or minus root 3. Okay, so sometimes these tangent ones are kind of tricky. So we know that root 3 looks like a unit circle value because we know that on the unit circle we have a lot of root 2s, root 3s, and so on. So we need to think about what values on the unit circle will actually have a tangent of root 3, whether it's positive or negative. So let's think about how we can actually get that. So we know that tangent of theta is equal to sine of theta over cosine of theta. And we want to get this to turn into root 3. So we're just going to ignore signs for a second so that we can just see how the numbers work out. So I know that I have a few pairs of numbers on the unit circle. I have root 3 over 2 and 1/2, and I have root 2 over 2 and root 2 over 2. So if I want to get root 3, I'm going to need that pair of root 3 over 2 and 1/2, but I need to decide what order they come in because that's going to determine my angle. So if I want to solve for tangent, I need sine to be that top number. So that means I need root 3 over 2 on the top, and I need 1/2 on the bottom. Okay, so what we see here is that sine is equal to root 3 over 2, and cosine is equal to 1/2. So the angle on the unit circle that has sine equal to root 3 over 2 is pi over 3. So from this, we get that theta is pi over 3. So we're looking for those angles on the unit circle that have those denominators of 3. So let's think about what those are. So in quadrant 1, we have pi over 3. In quadrant 2, we have 2 pi over 3. Quadrant 3, we have 4 pi over 3. And quadrant 4, we have 5 pi over 3. Okay. And the reason we get all 4 of these is because, again, we have both signs going on. So tangent can be both positive or negative, so we don't care. It can be in any quadrant we want. All right, so let's see if we can get our general solutions now. So the first thing we're going to do is start with our first solution that we got. So we're going to start with pi over 3. And we're going to ask ourselves, how much should we add to pi over 3 so that it hits something else on these 4 solutions? So if you notice, well, our function was tangent, so it's probably a good idea to add pi k. And let's talk about why this happens. So if we start with pi over 3 and we add pi, we're going to end up at 4 pi over 3. And if we add pi again, we're going to end back up at pi over 3, but it's going to just have a different name. And then if we add pi again, we'll go back to 4 pi over 3, just with a different name, and so on. So what's going to happen here is anytime your solutions form a straight line like this in pairs, that's going to correspond to one general solution with a period of pi. Okay, so we're going to add pi k, where k is an integer, and that takes care of this entire line right here. Okay? Now for our second general solution, we're going to start with a solution that's not on that line that we already took care of. So let's say we start with 2 pi over 3, and once again, we're just going to add all the multiples of pi that we can, and what that's going to do is that's going to take care of this line, because every time we add a multiple of pi, we're going to flip-flop between those 2 points. Okay, so these are our 2 general solutions for this example. All right, let's try a slightly trickier one. So this next one, we have 2 times cosine squared of theta minus 7 times cosine of theta plus 3 is equal to 0. Okay, so before we talk about solving this one with trig functions, I'm going to rewrite it in a way that might seem more familiar to you. So if I rewrote this as 2x squared minus 7x plus 3 is equal to 0, hopefully you've seen how to solve those types of equations before. So when we have a quadratic equation like this, where x has an exponent of 2, we know we have a couple of ways of doing that. We can factor, we can use quadratic formula, or we can complete the square. You always want to try and go for factoring first, especially when we're going to talk about these trig functions, because it's much easier to solve if you factor than if you use the other 2 methods. So we're going to try and factor this equation, but we're just going to factor the normal version first. So just a refresher, if we wanted to factor this, first we want to think about how to break up that first term. So we know that eventually we're going to get 2 sets of parentheses, and the only way that we can break up 2x squared is into 2x and x, because 2 only factors one way, into 2 and 1. Now we want to ask ourselves, how can we factor down the 3 so that when we FOIL these 2 parentheses back out, we get that middle term of negative 7x. So there's only one way to factor 3. We can factor it into 3 and 1. And since we want a negative 7, both of those factors need to be negative. So we want to put a negative 3 somewhere and a negative 1 somewhere. Well, if I put it here, if we FOIL this back out, the negative 3 and the 2 make a negative 6, minus another 1 gives us the negative 7. So this is the factorization that we want. Okay, so let's take this back now to the trig version of this. Okay, so I'm just going to kind of box this off because that's not really part of our problem. So if we're going to factor this equation with trig functions, it's going to be exactly the same as how we factored it with x's. The only difference is that cosine of theta is playing the role of x. So the way that we would factor this with the cosines in there is just 2 cosine of theta minus 1 times cosine of theta minus 3 is equal to 0. So if it helps you to factor equations like this, maybe rewrite it with x's and factor it that way, and then go back and put the cosines in if that's confusing. If it's not confusing, you're welcome to go ahead and factor it straight down into the two factors that I have here at the bottom. Okay, so our next step when we solve a quadratic equation, and we've already got it factored, is we want to take each of those factors and set them equal to 0. So we're going to do 2 times cosine of theta minus 1 is equal to 0, and cosine of theta minus 3 is equal to 0. And then we want to solve each of these little equations. So in this first one, we get 2 cosine of theta is equal to 1. So cosine of theta is equal to 1/2. And if we think about the angles on the unit circle that have a cosine of 1/2, we get that theta is pi over 3 and 5 pi over 3. So we want that angle in quadrant 1 and the angle in quadrant 4. For this other factor, we can add 3 to the other side, and we get that cosine of theta is equal to 3. Now there is a problem with this. The problem with this equation is that if you remember when we talked about cosine, we said that the biggest value that cosine can take on the unit circle is 1. So cosine can never be equal to 3, so this factor is going to give us no solution. Okay, so it's important to notice that even though we got no solution for one of the factors, that doesn't mean that your entire equation has no solution. We still got these two solutions of pi over 3 and 5 pi over 3, so those are the two that we would list if we were looking between 0 and 2 pi. But we're going to list our two general solutions since those were our directions here. So you wouldn't list no solution as your answer unless every factor gave you no solution. Okay, that's the only time you list no solution. So let's get the general solutions for this equation. So we're going to take our first answer of pi over 3, and since our function is cosine, we're just going to add 2 pi k, where k is an integer. And then we're going to have 5 pi over 3 plus 2 pi k, where k is an integer. And that's all there is to it. You just have to remember to add those extra little bits of the period and then every multiple being an integer. Okay, let's try one more of these basic equations and then we'll move on to some slightly tougher ones. So in this next example, we have cosine of theta, 5 sine of theta times cosine of theta plus 4 cosine of theta is equal to 0. So just like a regular equation, we want to find some way to possibly factor this. So a good hint is that it's equal to 0. So anytime an equation is already set equal to 0, it's a good indication to you that you should try to factor. And if you notice, we have a factor of cosine in the first term and a factor of cosine in the second term. So we can just factor out a cosine. So this turns into cosine of theta times 5 sine of theta plus 4 is equal to 0. So just like the previous example, now we have two factors that are multiplied together and they equal 0. So what we can do is we can break each factor off into its own equation. So we can say cosine of theta is equal to 0 and 5 times sine of theta plus 4 is equal to 0. Now cosine of theta equal to 0 tells us that theta must be pi over 2 or 3 pi over 2. And the second factor tells us that sine of theta must be negative 4 over 5, which tells us that theta is equal to sine inverse of negative 4 over 5. Okay, so let's see what's happened here. So the first factor gave us two values that were on the unit circle, but the second factor is going to be one where we'll have to use a calculator because 4 over 5 is not a unit circle value. So if we were to plug that in the calculator, we would get an answer of negative 0.92. And remember, we're going to talk about radians because that's what we're assuming for trigonometric equations. So we have one angle of negative 0.92. So let's think about where that is on our quadrants here. So negative 0.92 should be somewhere around here. It should be somewhere in quadrant 4. And if we were to find the positive version of that angle, we would get 5.36. Okay, so to do that, remember we just do 2 pi minus 0.92, and that gives us the angle going the other way around. So then we want the other angle that would have the same sign, but be in quadrant 3. And the way we can do that is we can think about, let's change colors. So we can think about this distance plus this distance. So this distance at the top must be 180, or pi. I should think about it in radians. Oops. Let's draw that axis back in. Okay, so we know that this angle at the top is pi because it just covers the first and second quadrants. This angle below the x-axis is going to be another 0.92. So to get our total angle, we're going to add pi plus 0.92, and that's going to give us approximately 4.07. Okay, so that's our two angles that come from the second factor. So now we need to write all of these answers as general solutions. So I'm going to take care of the pi over 2 and 3 pi over 2 first. So we'll have theta is equal to pi over 2 plus, so now let's think about what we need to add. So it might be a reflex for you to automatically add 2 pi because cosine's period is 2 pi. However, this is one special case where actually pi works better. So if we think about where pi over 2 and 3 pi over 2 are, let me draw this a little bit further this way. So if we think about pi over 2 being at the top and 3 pi over 2 being at the bottom, we notice that they're actually 180 degrees apart, or pi. So rather than writing two different general solutions, one for each of these, we can actually just write a single solution that takes both into account at the same time. And so what we do is we just add pi instead of 2 pi, and we say k is an integer. Okay, so that takes care of our first two answers over here. Now we just need to write general solutions for the second factor. So our first one, we're going to have theta equals 5.36 plus 2 pi k, where k is an integer. And then finally, we're going to have 4.07 plus 2 pi k, where k is an integer. So for these, they're not pi apart or 180 degrees apart, so we're going to have to write a general solution for each of them. So our final answer for all the general solutions of this equation are those three thetas that we came up with. Alrighty, let's move on to some slightly more difficult equations. So at the top here, I've just written some handy ideas for if you get stuck on solving equations. So these are some good things to try and see where you can get with them. So we always want to get a trig function by itself. Maybe adding some like terms will make it a little bit simpler for you. We already did a couple of examples where we factored, so that comes in handy a lot. And then sometimes you may have to substitute in some identities. So let's see some examples. So we're going to do just like we did with the previous page. We're going to solve some of them on 0 to 2 pi, and then we're going to solve some of them more generally. So in this first equation, we have 2 times sine of x times cosine of x is equal to sine of x. So let's ask ourselves how we could start to solve for this. So one thing you might notice is this 2 times sine of x times cosine of x. So if you remember from our section on double angle formulas, this is actually equal to sine of 2x. Okay, So your first instinct might be to go ahead and substitute an identity. Okay, so let's talk about why that actually won't help you very much. So let's start solving it. So if we were to substitute that and say sine of 2x is equal to sine of x, the question would be, where do we go from here? Well, maybe we could subtract over sine of x, but then we run into a problem because we can't factor that. So because our angles are different, so in one of the signs we have 2x, in another sign we have x, we can't factor that in any way. So this would not be a good idea. Okay? So this won't help us. So we need to think of something else. So maybe let's just subtract over the sine of x. So if we want to factor, we want to make sure that every single term is on one side of the equation and that we have 0 on the other side. That's very important. So maybe we can set this up to try and factor. So now that I've subtracted over sine of x, I see that I could factor out sine of x. So if I factor out a factor of sine of x, I'm left with 2 cosine of x minus 1 on the inside of the equation. And so now I have two factors that I can each set equal to 0. So I'll have sine of x is equal to 0, and 2 cosine of x minus 1 is equal to 0. So sine of x is equal to 0 gives me x is equal to 0 and pi. And then my second factor, I still need to do a little bit more solving. So cosine of x is equal to 1/2. So x is equal to pi over 3 and 5 pi over 3. Okay? And so these are my two sets of solutions. So I have 4 solutions to this equation. So this is a good example because it forces you to think about identities, but maybe how the identities won't help you. So just because you see an identity doesn't mean that you should substitute it. So always look for those, but then take a step back and ask yourself, if I substitute this, will it get me further in my problem? Okay? So it kind of goes back to that idea when we were doing proofs and we said, like, when we get stuck, sometimes we want to think about what we want to get to and how we're going to get there. And sometimes an identity may help you, sometimes it may not. So let's try another example. So in this one, we have cosine squared of x minus 3 sine of x minus 1 is equal to 0. So this one indicates to me that I probably am going to want to factor eventually because I have 0 on one side of the equation. However, as this equation stands, I cannot factor it because one of the terms has cosine, one of the terms has sine, so it just doesn't lend itself very nicely. So we want to think to ourselves, how can we make this factor? And if you're thinking that we want to get everything in terms of sine, that's probably a good idea. So we want to get rid of this cosine squared of x and turn it into something with sine in it. Okay? So let's think about how we can do that. So if you think back, so this is sort of an aside that we're going to talk about. So if we think about our Pythagorean identities, that's usually the first ones I jump to. We had this one that related cosine squared and sine squared. So we had cosine squared of x plus sine squared of x is equal to 1. And so this is actually kind of what we want, because if we just move over the sine of x, or the sine squared of x, we get that cosine squared of x is 1 minus sine squared of x. So now we have a way that we can rewrite cosine squared using only the sine function, and that's good. So let's make a substitution here. So in place of cosine squared, I'm going to write 1 minus sine squared of x, and then I'm just going to copy the rest of my equation. Okay, so I wrote parentheses around it just so you can see what has been substituted, but they're actually not necessary because we don't have anything here that's going to be distributed. So I'm going to go ahead and erase those now that you've seen the substitution. Oh, I'm erasing a lot more than I want. Okay. So now our equation looks like this. So now let's maybe just combine some like terms. So we see that we have a positive 1 and a negative 1. So those are going to add away. And we're left with negative sine squared of x minus 3 sine of x is equal to 0. So now I'm in a really good situation because I only have one trig function. I have sine, and I have everything on the same side of the equal sign, and I have 0 on the other side. So now I can factor like I wanted to do from the beginning. So I can factor out a common factor of negative sine of x, and the reason I'm factoring out the negative is just to get rid of some of these negatives. So notice since we have a negative in both terms, that will probably help our case a little bit more. So we're going to factor out negative sine of x, and we're going to be left with sine of x plus 3. And so we have our two factors equal to 0. So we can split this up as negative sine x equals 0 and sine x plus 3 equals 0. All right, so in the first factor, we can divide by the negative. So we get sine x is equal to 0, which tells me x is 0 and pi. And then in my second factor, I can subtract the 3. So we get sine x is negative 3. But here we run into the same problem as that one we did on the first page. So if you remember when we first talked about the unit circle, we said that the smallest value that sine can take on the unit circle is negative 1. So it's impossible for us to have a sine value of negative 3. So this factor is going to give us no solution. But once again, our entire equation still does have solutions of 0 and pi. So no solution, again, is not your answer unless every single factor gives you no solution. Okay. So let's try one more example on 0 to 2 pi, and then we'll do a few with general solutions. So this next one we have secant of x times tangent of x is equal to 4 times sine of x. So this one's a little tricky. So maybe I'll start by just turning everything into sines and cosines and see if I can get anything to cancel. So secant we know is 1 over cosine of x. Tangent is sine of x over cosine of x, and that's equal to 4 times sine of x. Okay, so I can multiply the two fractions on the left and get sine of x over cosine squared of x is equal to 4 times sine of x. All right, so now we're in a situation where we really don't know what to do. So maybe we can just subtract over the 4 sine of x and see if we can factor, because then we'll have a sine in both terms. So if we do that, we'll have sine of x over cosine squared x minus 4 sine x is equal to 0. Okay, so I can factor out a sine x. So we have sine x times 1 over cosine squared x minus 4 is equal to 0. Okay, this is good. So we have two factors. They're multiplied together. They equal 0. So let's take each one and set it equal to 0. So we have sine x is equal to 0, which tells us that x is equal to 0 and pi. So those are two answers. And then I'm going to write the other one up here because we're going to need to do a little more work. So we have 1 over cosine squared of x minus 4 is equal to 0. So we can go ahead and add over the 4. So we have 1 over cosine squared x equals 4. And then I can square root this. So we have 1 over cosine x is equal to plus or minus 2. So once again, don't forget that plus or minus sign when you take the square root. And so what we can do now is, since 1 over cosine x is equal to 2, we can say that cosine of x is equal to plus or minus 1/2. So we can basically flip both sides of the equation. And so now this is something that we should recognize from the unit circle. So the places on the unit circle where the cosine is 1/2, regardless of whether it's positive or negative, are going to be all those angles with denominators of 3. So those 4 angles are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. So from that second factor, we get 4 solutions. And so in total, we have 6 solutions for this equation. And so we have the 0 and pi, and we also have all those angles of denominator 3. Alrighty, let's move on and talk about some general solutions. So, like I said, in all of these, we're going to find all solutions to the following equations. So in this first one, we have 3 times cosine of x plus 1 is equal to cosine of 2x. All right, so this one, maybe we're thinking factor, but we kind of ran into that problem we did with number 1 on the other column, is that we talked about why having sine of 2x would not be beneficial to us. So this is kind of the same thing. We've got this cosine of 2x showing up, and we know that that's not really going to help us because we won't be able to factor anything if our two cosine functions have different angles. So we want to find some way to substitute that cosine of 2x. So if you remember from the section on identities, we had 3 choices for cosine of 2x. And so here we want to think about how do we make a decision between those 3 choices. One of them is going to help us much more than the other 2. So how do we choose? Well, if our ultimate goal is to factor, we know that we need the formula that has the same trig function that we have in our equation. So our equation contains cosine of x, so we probably want to pick the one that contains cosine of x. And there are actually 2 of those, but one of them has sine as well, and that's not going to help us as much. So we want cosine x only so we can, and I'm going to have to factor. Okay, so I got to make my little box a little bigger. Okay, so just to recap, we have 3 choices to substitute for cosine of 2x. We want to ask ourselves, how do we choose between those 3 choices? Well, we know eventually we're probably going to want to factor, so we need the trig function in our equation, which is cosine of x. So we want to pick the one that only has cosine of x, so that we'll be able to factor. Okay, so let's make that substitution. So this turns into 3 cosine of x plus 1 is equal to 2 cosine squared of x minus 1. So that's our substitution for cosine of 2x. Now I can move everything to one side. So I can move over the 3 cosine x and the positive 1 to get 0 on the left, and I'll have 2 cosine squared x minus 3 cosine x minus 2 on the right. And now I have something that factors quite nicely. So if we want to factor this, we'll have 2 factors. And first we want to think about how do we break up that 2 in the first term. Well, there's only one way to do that. So one factor is going to get 2 cosine of x, and the other factor is just going to get cosine of x. All right, and then we want to think about how can we break up negative 2 so that when we FOIL this back out, it gives us that negative 3 in the middle term. So there's only one way to factor negative 2. It's into 2 and 1. One of the factors is going to be positive, one of them is going to be negative. So if we make the 2 negative, that'll give us negative 4, and then we can add 1 back to give us negative 3. So if we FOIL these 2 factors back out, you'd see what we get with what we started. Okay, so let's take each factor, set it equal to 0. So 2 cosine x plus 1 equals 0. Cosine x minus 2 equals 0. So the first factor, we get cosine x is equal to negative 1/2. The second factor, we get cosine x is equal to 2. So cosine x is equal to negative 1/2 tells us that x is equal to 2 pi over 3 and 4 pi over 3. And cosine x equal to 2, we have no solution. So if I want to write my general solutions now, I just need to write one for each of my two solutions from the first factor. So we can start with x is equal to 2 pi over 3 plus 2 pi k, where k is an integer. That's kind of squished. Sorry about that. Let's see if I can squeeze it in there. We'll write it here. And then my second one, I'm going to get x is equal to 4 pi over 3 plus 2 pi k, where k is an integer. All right, so those are my two general solutions for this equation. So in this next one, we have sine squared of x times 1 minus sine squared of x plus cosine squared of x times 1 minus sine squared of x is equal to 0. So let's see what we can do. So you might notice that we have this repeated factor over here of 1 minus sine squared of x. So we can factor that out as a common factor in both terms, and we end up with this. So we get 1 minus sine squared of x times sine squared of x plus cosine squared of x is equal to 0. So this is also called factor by grouping, if you've heard of that before. So I'll make a little note of that. Okay, so now we have two factors. They're multiplied together. They equal 0, so we can solve each of them. So we have 1 minus sine squared x equals 0, and sine squared x plus cosine squared x equals 0. So maybe let's start with the first one. So we could go ahead and move the sine squared x over, or we could say that 1 minus sine squared x is just cosine squared x, and that's equal to 0. So if we square root both sides, cosine x, again, equals 0, which gives us that x must be pi over 2 and 3 pi over 2. In the second factor, sine squared x plus cosine squared x gives us that Pythagorean identity, which we know is equal to 1, which says that 1 equals 0. Well, this is absurd. 1 cannot equal 0, so we get that this has no solution. Okay, so our two solutions so far for this equation are pi over 2 and 3 pi over 2. So once again, let's think about where those are on the unit circle. So pi over 2 is at the top, 3 pi over 2 is at the bottom. So they're pi apart, okay? They both lie on a straight line that connects the two. So instead of writing two separate general solutions, we can combine them into one. And we kind of talked about this in one of the other examples. So we can say that x is pi over 2, and then instead of adding 2 pi k, we can just add pi k because they both lie on the same line where k is an integer. So our general solution for number 2 is going to be that. All right, we just have a couple more examples. I know this is a long section, but I want to make sure that you see plenty of examples of all the different kinds of equations. So in this next one, we have 2 times sine of 3 theta plus 1 is equal to 0. So this one's a little different. So we've got that multiple angle hanging around in there, but we're actually not going to substitute this one for something else. So since we only have a single trig function, we could just as easily get that trig function by itself as trying to, substitute something and make this super complicated. So let's solve this as if we just had a sine of theta. So if we had just a theta in there, we'd move over the 1 and divide by 2. So we can say sine of 3 theta is equal to negative 1/2. So I want to keep solving this just like I would with any other equation. And we're going to ignore the fact that we have a 3 theta for now. We're just going to play like it's theta. So if I was going to solve this, I'd want to ask myself what angle has a sine of negative 1/2. And that would be 4 pi over 3 or 5 pi over 3. So the big difference is instead of theta being 4 pi over 3 or 5 pi over 3, we're going to have 3 theta is equal to 4 pi over 3 and 5 pi over 3 because that's the expression inside of sine. All right? So those are our 2 answers so far. Oh, come on. Erase the parentheses. Thank you. Okay, so we have sine 3 theta equals 1/2, and so 3 theta are those 2 answers. So when you have a situation with a multiple angle, as soon as you get those 2 initial solutions, write out a general solution for each of them. So we're going to say 3 theta is equal to 4 pi over 3 plus 2 pi k, and 3 theta is equal to 5 pi over 3 plus 2 pi k. And the reason we do this is we still need to divide by 3 to get theta by itself. But when we do that, we not only divide the angle, we divide the period as well. So when we divide by 3, we're going to get theta is equal to 4 pi over 9 plus 2 pi over 3 times k. And the other solution, we're going to get theta is equal to 5 pi over 3 plus 2 pi over 3 times k. So these are our 2 general solutions. Okay, so notice again, when you have a multiple angle problem such as this, the very first thing you do is write out a general solution, because when you divide by that coefficient on theta, it's going to divide the angle as well as the period. All right, so very quickly, even though the directions just said find all solutions, I want to talk very briefly about how to find the solutions on 0 to 2 pi. Because with a multiple angle, it's a little different because we've got these weird general solutions. So on 0 to 2 pi, what we do is we're going to use these general solutions basically as formulas to get all of the angles that lie between 0 and 2 pi. Oh, and look at me. I forgot to say that k was an integer. Not following my own directions. Okay, so k is an integer there. And then k is also an integer over here. All right, so back to our 0 to 2 pi discussion. So once again, these general solutions are going to be formulas to help us get the things between 0 and 2 pi. So we're going to start by writing down the first 2 solutions. That should be a 9. That we had. So 4 pi over 9 and 5 pi over 9. And what we're going to do is we're going to add 2 pi over 3 to these 2 solutions until we leave the interval that we want. So 2 pi over 3 is the same as 6 pi over 9. So I'm just going to make a little note of that. 2 pi over 3 is 6 pi over 9. So we're going to add 6 to the top of each fraction until we leave 2 pi. So 4 plus 6 gives us 10 pi over 9. 10 plus 6 gives us 16 pi over 9. But if I were to add 6 again, I would get, what, 22? 22 pi over 9 is bigger than 2 pi. 2 pi is just 18 pi over 9. So this first solution, I'm done once I reach 16 pi over 9. The second solution, we have 5 pi over 9. If I add 6, I'm going to get 11 pi over 9. Add 6 again, I'm going to get 17 pi over 9. But if I add 6 again, I'm going to be bigger than 2 pi. So I want to stop at 17 pi over 9. So these 6 solutions are solutions between 0 and 2 pi. All right, so we have one more example. Well, actually, before we do that last example, let me just make a little note over here. So add 2 pi over 3 until you pass, or I should say reach, because we don't want to put anything bigger than 2 pi. Okay, so add 2 pi over 3 until you reach 2 pi. All right, so now on to our last example. So we have tangent of theta over 4 plus root 3 is equal to 0. So just like the previous example, we're going to treat this equation as if the theta over 4 is just along for the ride. All right, we're not going to worry about it until we get to the very end. So if I was just going to solve this, I'd have tangent of theta over 4 is equal to negative root 3. And so then I want to ask myself, which angles on the unit circle have a tangent of negative root 3? So the angle that has a tangent of negative root 3 is going to be, oh, I think my notes may be wrong on this one. Okay, tangent is negative will be in the second quadrant, so it should be 2 pi over 3. So we have theta over 4 is equal to 2 pi over 3, as well as 5 pi over 3. So this would be the second quadrant angle. This would be the fourth quadrant angle. My eraser's acting up today. Okay, so those would be our two solutions. So let's think about really quickly where those are. So 2 pi over 3 is up here. 5 pi over 3 is down here. So they lie on that same line going through the origin. So when we write out the general solution, we can just do one general solution that takes both of these into account. So we can say theta over 4 is equal to 2 pi over 3 plus pi k, and we'll leave out the k as an integer just for now while we have one step left to do. All right, so our last step is to get theta by itself. So we're going to multiply by 4. So we have theta is equal to 8 pi over 3 plus 4 pi k, where k is an integer. So this is our general solution. And then again, I just want to give you one more example if we were going to solve on 0 to 2 pi. So on 0 to 2 pi, remember we want to start with that fundamental solution that's in our general solution. So we're going to start with 8 pi over 3. And we're going to ask ourselves, well, if we add 4 pi, what happens? Well, if we add 4 pi, that's clearly going to be bigger than 2 pi because we're adding more than 2 pi to begin with. Same if we were to subtract 4 pi. That would again put us out of our interval because it's way bigger than 2 pi to start with. So the only solution on 0 to 2 pi would be 8 pi over 3. And so just to make a little note, as soon as we add or subtract 4 pi, we leave the interval. So that's why we only have one solution. Okay, so if you have any questions on solving trigonometric equations, please ask, because some of them can be really tricky. Just like when we did the proofs, sometimes you really have to be very familiar with all these different little tricks you can do and know which one to apply in which situation. So if you have any questions, please let me know. And this concludes our 7.5 lesson.